Okay, so before we prove the theorem, there's just one definition that's going to come up in the proof of that theorem. So we say that a function is of exponential order, alpha, if there exists some positive constants c and t, so that f of t is bounded by this exponential function. And so I think the best way to understand this definition is to just take a look at some examples. So if we are, for example, considering the function cosine 5t times e to the 7t, we would say this function has exponential order equal to 7, because for large values of t, this cosine function is bounded between plus or minus 1. So the absolute value of f is going to be, we can write this like so, is going to be less than, for example, 2 times e to the 7t. So therefore, there's our constant c. We can set c equal to 2, and this is going to be true actually for all values of t, lowercase t. So that function for large values of t is going to be bounded by an exponential function with power 7t. An expression like e to the t squared, this is not going to be bounded by any exponential function, since t squared is never going to be bounded by alpha times t. So t squared grows faster. Quadratic things grow faster for large values of t than linear things go. So e to the t squared does not have an exponential order. So just informally, all we're saying is if a function has exponential order alpha, that means for large values of t, its absolute value is going to be less than some constant times e to the alpha t. So that's going to be a useful property when we take a look at the proof in the next couple slides. Okay, so we are going to start this proof of the theorem about when we take the Laplace transforms of higher order derivatives of a function. So we're going to start with the first case when n is equal to 1, where n is the power or the derivative that we're taking, the order of the derivative. So if n equals 1, we want to calculate what is the Laplace transform of f prime. And we'd like to show this is what the theorem claims it should be. So let's assume we've got our function f. It's continuous on for non-negative values of t. So is its derivative. And we're going to assume that both of these functions, f and f prime, are of exponential order alpha, which we just discussed in the previous slide. So that means they are bounded by something that looks like c times e to the alpha t. So let's see what we would start with. If I want to calculate the Laplace transform of f prime, then all we're stating here, this is the definition of the Laplace transform, right? We would take e to the minus st times whatever function we want to take the Laplace transform of. And so now, again, we're not supposed to assume the thing that we're trying to prove. These are the only things that we can assume. So how could I integrate this? Well, I've got something times a derivative, so this looks like it might be a good candidate for integration by parts, and in fact it is. So I could, for example, set u equal to e to the minus st, and I could set v prime equal to f prime. Then u prime in this case would give us minus s times e to the minus st, and v would be the integral of that, which would be f of t. And so now by integration by parts, we're going to get u times v, and that's this term over here. So we're going to evaluate uv from the upper limit of n going towards infinity and a lower limit of 0. And for the other term, we would have u prime times v. So we would want to integrate from 0 to infinity s e to the minus st f of t dt. And that's where this comes from over here. If we pull the s out from inside the integral, then what's left is e to the minus st times f of t, which is, by definition, the Laplace transform of f of t. So that was the key step here. So really, proving it for the case for n equals 1 is just an application of integration by parts. Okay, so now let's just take a little detour and see how the fact that we are given f is of exponential order alpha comes into play. So what this means is that the absolute value of f of t is less than some positive constant c times e to the alpha t, we'll just say for large values of t. So for this limit that we have, if I want to calculate the limit as n goes to infinity, so for the upper limit, we're going to take n and plug it in place of this t and plug it in place of that t. So we're calculating the limit as n goes to infinity of f of n times e to the minus s times n. Okay, and what I'm going to hope to show is that this limit that we have over here, that this limit is actually equal to 0. And from the fact that f is of exponential order alpha, I know that this is going to be less than some constant c times e to the alpha t. So I'm going to replace this and just note that this limit is going to be bigger than this one because this is a little bigger than that. But at least I can replace fn with something more concrete, something that's exponential. And now we can just regroup our exponential terms inside this limit, and we see that the limit as n goes to infinity of c times minus s minus alpha times n. And this limit as n goes to infinity actually does approach 0. This will head to 0, provided that we're taking e to a large negative numbered power. So as long as s minus alpha is a positive number, that's going to guarantee that this power up here is going to have to be positive. So if this is positive, n is going to infinity, that's positive, and we have a negative sign, then we've got e to a large negative value, and that's why this is heading to 0 as long as s minus alpha is a positive number. Okay, so looking at what we have here, if I were to plug in the limits at 0 and infinity, first I would plug in n, and I would get this, and then I would subtract what I get when I plug in 0, which would be f of 0 times e to the 0, so that's just f of 0. And we just showed, because we have assumed that f is of exponential order, that this limit actually heads to 0. So this term goes away, and all that's left over is s times f of s, the Laplace transform, minus f of 0. So that's exactly what we wanted to show. So that's our proof there. So really, there's only two things going on here, and that's we had to use integration by parts to evaluate the integral, and then we had to use the fact that f was of exponential order to show that the limit heads to 0 as long as s is bigger than alpha. So now we've got the case for n equals 1. In the next video, I'm going to wrap up this proof using induction. So we've proven the n equals 1 case. If we assume it's true for n equals k, we'll then prove that it's true for n equals k plus 1.